Okay, so I recorded the entire demo explaining the concept of differentiation, but unfortunately my laptop's audio crashed and it didn't record anything. But the good thing is I clearly went over time in the demo, so I will try my best to cover everything within the given time constraint of the demo. So this video is definitely going to be it's definitely going to feel a bit rushed, but that's how the demo goes because it's not the actual video. So what I did is to explain the idea of differentiation, I first took this distance time graph where I have my time on x-axis, my distance on y-axis, and I ask what will be the velocity at this instance for. Uh, to this question, what a lot of the students do is they directly apply this formula of velocity, which they are familiar with in their physics course or whether they're in their mechanics course. They do displacement divided by time, that is 16 divided by 4, which gives 4 meter per second. But this is wrong. This is not giving me the instant velocity at this interval 4, but rather it's calculating the average from this 0 till 4. So essentially, it's giving me the slope of this line from 0 to 4. So this 4 is the slope of this line. But you can see that this line is way above this curved line. So it must be averaging out whatever this black line is showing, right? So now to this question, whenever I say this is the average velocity, a lot of the students states that, okay, but we only took one displacement at one time. How come we get an average? Because an average is between two quantities, right? So that is something which is hidden in the formula of velocity, which is d2 minus d1 upon t2 minus t1, where d1 and t1, your starting points, your distance was 0, and your time was also 0 at the starting point. So this formula shrinked into this formula. So that's why. So basically, we're calculating the average from this 0 till 4 for this thing. But differentiation helps you calculate the velocity at a specific instance. For example, if I ask you, okay, I'm not interested in the average velocity, I want to know the instant velocity at this point 4, or let's say this point 3, or this straight cross. I just want to know at this specific point. So what I will be doing is I will first get to the formal definition of differentiation, of course, so that in order to understand how I can get this instant velocity. This is, of course, the book's definition of differentiation. So again, imagine this is a distance time graph or any graph where this quantity is on y-axis. Let's say this is y and this is x, and then you have some arbitrary points x and x plus h. So x plus h is some point beyond x. Now, why I chose this x plus h, I'll be explaining that why specific this you can say why specific this quotation. It could be anything else. It could have been let's say x2 x1 x2, but why specifically x plus h, I will explain that later on. So I have these 2 points and I'm interested at their y value. So again, I'll be plugging this x into some function so that I can get the value. Similarly, for x plus h, I'm doing the same exact thing. I'm plugging this into a function x plus h where I'm getting this distance. One key point to remember here is these two f's are essentially functions are the same functions, so that they are representing the same y values or the y axis. Now, if I ask you, okay, then what is the average change? Since we just discussed what is the definition of average change, what is the average change between these two quantities? So you will do, okay, your change in y was f of x plus h minus f of x, your final change minus your initial change. Similarly, for x-axis, your final change minus your initial change, which was x plus h minus x. Now, this positive x and negative x gets cancelled out, and you will be left with, ignore this limit for now, you will be left with f of x plus h minus f of x upon h. So this is giving you the average change between these two quantities, or you can say now this is giving you the slope of this line, this colorful line. But again, this is not giving me the velocity at this specific instant x or x plus h. I wasn't interested in that. That's why I was trying to get to the definition of differentiation. So what differentiation tells you is you just take your formula for the average and then you apply limit where your h is approaching 0, or essentially your change in x is very small. Now, what this is saying? It's saying if your h is very small, let's say h could be 0.00000 till 1 up till so on, so it is a very small value of h. And if you observe here, I said x plus h. Now, if this h is very small and I'm adding in x, this means that I am actually at this point x, or a very close value around this x. So this formula is saying you are at x because your h is very small. You are essentially standing at x, and then for this x, you are getting this change in y. So this will give you your instantaneous velocity. So if I zoom in this x, the bigger picture of it, if I just zoom in this specific point, so let's say I have this slope that is given here, this slope. I have zoomed in this x. So I have this starting point which was x, and then this ending point was x plus h, where this h is very small. So this change is also very small, and this for very small change, I will also have very small y change, right? So this is giving me the instantaneous velocity. It's saying you are standing exactly at x, or you're going very small distance far from x. So you're getting this change in y, and you are getting the instantaneous velocity. It is again the average velocity, but since we have shrinked my x to be very small, that average is essentially converting into instantaneous. So that's why it was very important to first get the idea of average velocity and then the instantaneous velocity. Now, similarly, if we look at this formula, the average velocity, this will be telling you, this is saying that your time is very small, or you are shrinking your time to be very small. So you will be taking a very small time interval if you wanted to calculate this instantaneous velocity, which I first asked while starting this lecture or this demo. So I was interested exactly at this point four. So now the instantaneous velocity would be okay, you are not going all the way back to zero. You will only get some very small change somewhat over here. And then for this very small change, you will detect a very small change in your y value. This will be this very small change in your y value. And then this will give you the instantaneous velocity. Now, this instantaneous velocity, since it's a parabolic graph, it's x square. Of course, you will be understanding this further into the course, but since I know this is the graph of x square, and then the derivative of x square, or or the differentiation of x square is 2x, and then if you're interested at this specific point, this will be 2 times 4, which will be 8. Now you can see, even though the average velocity was giving me 4 meter per second, but exactly at this specific instance 4, my velocity is 8 meter per second. So this also helps you to get the picture of what exactly average and instantaneous is doing. The average is taking the overall change that was happening in this. So the car speed was first very slow, and then it went very fast. So the average would be slow plus fast divided by 2. So that is somewhere between, which was 4. But if you look exactly at 4, your car was traveling very fast, and this is obvious because your curve went straight at this point. So your car must be traveling very fast. So that's what differentiation is telling you, and that's how differentiation comes handy. So you don't have to worry what I did here. I just wanted to explain it. You will be understanding it later into the course. The only thing that was important here was this formal definition of differentiation, that is your change in y upon your change in x, but your change in x, you have shrinked it to be very small. So you are, instead of getting average in velocity or average value, you are now getting instantaneous value. I hope you guys were able to understand this, and yeah, that was it for the demo. Thank you.